My name is Clifford Schoff, and I am a problem solver. And I am going to talk to you today about solving problems. I spent 30 years at PPG, Pittsburgh Paints, and been retired for nearly 20 years, but did a lot of teaching and problem solving as a consultant during that time. Here's a list of typical paint application problems and defects. And I'm going to talk about application problems, but also field problems. And many of you will have experienced and been extremely irritated by cratering, which is one of the most common defects. And de-wetting and cratering is often a form of de-wetting. If you are dealing with bake coating, solvent popping and wrinkling may occur. Flooding and floating and Baynard cells are similar defects that occur due to convection flow. And orange peel is where you get a bumpy surface. And years ago in the US, people were happy to have their automobiles have orange peel because they thought that it meant a thick coating that would last a long time. But nowadays we try to make a smooth coating. Sagging with liquid paint that gives sag marks. We especially ran into problems with sagging with high solids coatings. They would not sag when you applied them, but they would sag when they were baked. And then pinholes, which can be a form of cratering or solvent popping, and can be, or air and inclusion. Here's some of the defects. The top left hand is a classic crater. And it's on on an aluminum substrate that's a test panel. To the right of it is de-wetting of a red coating from a white primer. The lower left is, if you look at it, you might say, well, that's another crater. But it's hard to tell. You don't always know whether you're dealing with a crater or a pop. In this case, this was a solvent pop. But not only that, you want to know where the volatiles are coming from. Did they come from underneath the paint, for instance, with a plastic substrate that may contain volatiles? Or are they somewhere in one of the layers of the paint? To the right is an example of wrinkling, where the coating was applied, but when it was, and this usually is with a bake coating, and when it baked, it formed these wrinkles. Field defects, there are so many different ones. It depends on what kind of coating. With automobiles, loss of gloss has always been a problem. Chalking occurs on houses. Blushing is where water is picked up and changes the color of the paint. Blistering appears when a paint is, in fact, has water on it, and sometimes in sun. Freshly painted surface will form blisters. Air pollution has been noted for causing water spotting and acid etch, especially acid rain. Cracking, checking, spalling, all are related. Delamination. Coatings can be stressed during heating process, baking process. biological attack would be where insects, bird droppings, various other biological materials may fall onto the coating, which may change its gloss, may change its, make actual defects, more like, say, the acid etch up further there would. And then color changes, for probably the classic example being fading of red coating to give a pink coating. Abrasion, mar, and scratch. Some problems with abrasion are because, for instance, automotive customers like to do things that cause damage, and they wonder why the paint doesn't hold up. Impacts and chipping, and then one that used to be a very big problem, especially in countries where they put salt on the roads, not so bad now, is corrosion. Here's some field defects. The blistering on the upper left-hand side, cracking. You often get the sort of three-corner cracks, and then at the bottom is corrosion, and the little sort of worm tracks that are coming up from the corroded area, the joint there, are what we call filiform corrosion. And that's an interesting process and defect in itself. One of the things I want to teach you most about is attacking problems. And the first thing is to identify the problem or defect. And you may say, well, it's easy, I know what it is. Well, it's critical to do this accurately before going and going to solutions, to countermeasures. And be sure to see the failure firsthand. If you're a person working in a lab, people may say, oh, I've got this cratering problem, what can I do? But you need to find out, is it really cratering, or is it some other defect that looks like a crater? And do not assume anything. Do not assume that the paint was made properly, that it was cured properly, that there were no contaminations in the area, etc. People may say this, but make sure you see what the situation really is. Ask a lot of questions and obtain as much background information as you can get, but the difficulty is sometimes you get misinformation. And then apply root cause analysis if possible, and I'll talk about root cause analysis in a moment. Identification, the first thing usually is just looking. And if you're very experienced, you look, you may well be able to determine what the defect is, or the problem is. But be careful, you may be fooled. I've been fooled more than once, I can tell you that. I often use the hand lens or a shop microscope. They're very useful, and nowadays there are microscopes that are more like a cell phone, and that can allow you to see the image of the defect, but also to save the image and use it like a camera, really. Documentation of the problem, if you can go to where the defects are occurring, or the plant or the site, photograph it, document possible areas of contamination, so on. If possible, bring examples of the defect to the lab. Bring a piece of hood of a vehicle. Bring pieces of wood that show where the wood paint, the painting of wood has produced defects. If you can bring these to the lab, then examine them by light microscopy. This is the most powerful tool that you can possibly have. And you may be doing cross sections and then examining the cross sections. If you have access to scanning electron microscopy to SEM, that's great. But light microscopy can accomplish a great deal. I mentioned root cause analysis. This is the determination of the basic or underlying cause of a defect or problem. This comes to us from the Japanese, who practice this and have certainly taught many people in the US to practice this if you want to be customers of theirs. It involves identifying the cause and proving that it is the cause. So it takes more discipline, more experimentation, and more documentation than normal problem solving. And you don't always have time to do this. But if it's done correctly, then the countermeasures that you develop guarantee that the problem will not happen again. So for application defects and the problems, I used to use light microscopy a lot. I'd look at the defect. If there was a color problem, I'd look at the pigment particle size in the wet paint and whether it was flocculated. If there was dirt in the coating, I would identify it. I might look at it in the wet paint, but usually if there is dirt, it is coming from the customer's plant or from the area where the painting is being done, for instance, a building or a house. Very rarely is in the paint. May need to examine a cross-section of a pop or a pinhole to see whether the volatiles come from the substrate or the coating. If there's poor adhesion and paint chips are coming off, or you can pull them off, look at the back with the microscope. You can see if the failure was adhesive, that is, the chip has come right off the substrate, or cohesive, where the chip is actually, the paint has come apart and failed. If there's, for instance, with a wood coating, if there's a layer of wood fibers on the back of the coating, then the wood substrate may have been degraded before painting. And certainly you're getting a cohesive failure. Field problems are difficult because there are so many possibilities of causes. And the person doing the work has to determine whether the problem is due to the design of the painted object. It may be something that's going to have problems no matter what. And I've seen this with designs of, for instance, automotive hoods or bonnets of automotive of cars, and also substrate or surface preparation. For instance, poor cleaning or poor pre-treatment or just a dirty surface. Is the defect due to the fact that the wrong paint was used, or there was a layer missing, no primer is there? And the other problems include the process of the application. Uh, the cure, was there over baking? Was there under baking? Was the painting done outdoors in the sun so it dried very quickly? I learned the hard way that painting an automobile in the sun produces a very rough surface. In the rain, I painted a house and it rained immediately afterward, and a lot of the paint ended up on the ground. This was a waterborne coating that was essentially dissolved by the rain. And where the required coats apply, well, all of them applied. Where they applied when they were supposed to be applied. And then repairs after application. If the coating has to be sanded and repainted, and then say if it's baked, a high temperature bake can cause problems, or low temperature bake. You may have to do physical testing comparing the problem coating and a control. Here's a list of some of the physical testing, and then chemical testing. And one of the difficulties is when you see differences, were they because the original problem coating had something wrong with it, or was it just something that happened out in the field, maybe particularly high temperatures, very powerful sunlight in, say, someplace like Australia or desert area of the United States. An adhesion failure, I mentioned before, looking at the back of paint chips. Determining causes, back again to observation. You look at the failure by eye and under magnification. Now, often when we have paint that has been saved, we'll look at the wet paint and compare that to a control. Something that with industrial coatings, say often called OEM, automotive coatings, a lot of industrial coatings. I would go to a plant, or service people would go and look at see whether the substrate preparation was acceptable, what the application was like, what were the work practices. Were people careful and the plant clean, or was it dirty? And not surprising that there were sources of contamination. If they're on-site applications such as auto refinish or maintenance or architectural, visit the site, observe everything, keep your eyes open, keep thinking. Your job is really to use your eyes and your mind to find out why the defects are occurring. And something I tell people is be a detective. Detectives look for causes of crimes, or where crimes have occurred. Well, you're looking not at a crime, but at something that may have similar sorts of results and similar sorts of causes. Often it is useful to recreate defects. And we usually use panels that we buy, or in some cases you make them from steel or aluminum or wood. But if possible, use the customer's substrate. I actually cut up a car body so that I could have exactly the same substrate the customer was using, because we never saw the defect when we used the panels that we bought, but we saw it on the automobiles. If possible, apply the paint with similar equipment, same kind of spray gun, similar techniques that the customer uses. If you don't have what the customer uses, well, that's not the end of the world, but it always helps to have the right equipment. Go to the customer and look at the application of the paint and the appearance of the panels or parts. In my lab, we used to do hot plate bakes. We'd observe the drying and curing of a coating by putting a coupon that we painted. We put it on a hot plate where we could control the temperature quite well, and we'd use a low power microscope, usually with the camera. Sometimes it's just the camera, in order to save what we saw doing these hot plate bakes. Finally, getting to solving the problem. Once you have evidence for the cause of the problem, you've got to decide on solution, a countermeasure, and try it. Now, one of the difficulties I've had with fellow workers is that when it didn't work, they'd say, "Oh, that's no good." But negative results can be useful. They give you possible boundaries. You know that you have a space where there are things that fail, but you have a space where you're looking for things that do solve the problem. And negative results usually can point you to a possible solution, as well as trying to getting something that really works. And then you want to try things until you have a workable solution, documented carefully. If you can find out why the solution works, if you do that, that will enable you or help you establish the root cause. And then try the countermeasure in the paint plant, if it's a matter of an additive or different order of addition of the paint, or try it online. When I first started working in auto plants, I was horrified to see that people will do experiments online. They will do additives to the paint, change the paint on a trial basis, and sometimes it worked, sometimes it didn't. Fortunately, it never seemed to damage the paint or make it so that it was worse. But if what you've done works, you implement it into the product or the process. So in conclusion, effective problem solving depends on careful observation and accurate identification of the defect or failure. The most useful tools in problem solving are your eyes, augmented by a light microscope, and your mind. Once you establish what the problem is, then you can work on determining the cause. Once you are certain of the cause, then you can work on solutions to the problem. When you find a solution, document it and try to figure out how it works. Change the problem or process to make use of the solution. In the program, where this talk will be part of, there should be a little bit of time to ask questions, and I hope to be there via Zoom. But if you have questions and they haven't been answered, then this is my email address: c_schoff40@ms.com. I promise to answer your emails. I may or may not be able to solve your problem, but I'll try to help. Thank you.
Thank you, Dr. Schoff, for this impressive and useful presentation. Now we can move to the question and answer part.
Does anyone have a question?
Yes. Now there's one first question. I'm just reading it. Is there a method you can recommend to solve the rubout problem, especially in gray colors, in mid-range, interior, in decorative paints?
Oh, that's a tough question. I would have to talk back and forth with you, I think, to find out more about the product and what the problem looks like. But if you send me an email, we can see what we can do about discussing this.
Thank you. In the meantime, I have a question for you. Which was the biggest problem in your lifetime in the industry? Let's say a challenge you ever faced, you remember, and how you solve it?
Well, I would say the most unusual problem is I walked into a truck plant in Mexico, and guy said, Cliff, we have a big problem. The white trucks are coming out pink, and the big pickup trucks that they build mostly for sale in the U.S. They're very macho. They're people who buy them are really the men who buy them who are really showing off in most cases. But he said pink no es macho. Pink is not macho. So I looked, and it wasn't bright pink anywhere, but definitely there was a pink cast when I was at the end of the line. And what I did was when we have a red coating, we often have trouble with that color changing and fading. Mm-hmm. So I thought, well, let's see, we'll paint some big panels and put them out, and after we bake them, we'll put them out in the sun. This was in northern Mexico, where there's lots of sun, and so we put these panels out, and it definitely had this pink cast, and we put them out. I think it was all morning, maybe longer, and then lo and behold, the pink was gone. Mm-hmm. So we actually took probably 100 truck bodies on whatever we could put them on, and put them out in the parking lot, or as many parking lots as we could take over, and got them to change back to white. And we changed the paint, and later on we found out that that there was one of the components of the solvent that was used to reduce the paint, was to reduce the viscosity, was causing this problem. But I'm not sure we ever found out exactly what the root cause was. What was the material that was in that reducing solvent? But that one was an interesting one. We joked about, selling them as pink trucks or whatever, and the plant manager said, if you let any of those trucks out of the plant, I will kill you.
Yeah. Okay, thank you for this explanation also. It was very useful for most of us. And one more question from Mr. Engin Törüşlü. Thanks a lot. What types of equipment do you suggest field technicians should take along themselves when they are investigating field problems?
Well, I would take, I would have a hand lens, just a little hand lens. I had a small microscope, shop microscope of 40 power. Some people like higher power ones, but they're harder to focus if you're on looking at the hood of a car or the side of a house or something like that. Those were the most useful, and there now are uh, microscopes that I mentioned in the talk that sort of a built-in microscope and camera that's like a cell phone that can be used. But you want to be able to document the defect. You don't want to just take notes. You want to have a picture of the defect so that you can go back to if you can't take a piece of whatever it is back, which is often happens. But if you bring the picture back, and if the problems are bad enough, for instance, we had a big acid rain problem. Oh, that's probably 30 years ago. And we had to cut pieces out of cars so that we could analyze the acid etch in when we brought them back to the lab.
Thank you. Is there a quantitative method to determine the internal stress that is developed in the cured film?
Sorry, say that again.
Is there a quantitative method to determine the internal stress that is developed in the cured film?
Yes, there are techniques for that. There's actually an instrument that can be used to by changing the temperature and or the humidity. You have essentially a thin piece of metal that you apply paint to, and then you control the humidity. There's sort of a box that you control the humidity and temperature, and you can look at the effect of humidity and temperature, and you find sometimes that some coatings will that bar will it's thin, but it will essentially bend way up or way down depending on the situation. And you can determine how much change there is, and what the effect of formulation, additives, things like that do. Okay. But again, if I could give you, anyone who wants to know more, I could give you details on this technique.
Yeah, by email, they can reach you.
Yes.
Another question, what kind of binder pigment systems can be suitable for composite, aviation, and aerospace industry?
Sorry, say that again.
What kind of binder pigment system? A system is asked to us, can be suitable for composite, aviation, and aerospace industry.
Well, that kind of system is really quite different from most of the ones I worked with. I had some experience with aerospace. I could find out that information, but I don't have that off the top of my head. I can't give that. But certainly dispersion is very important, and controlling dispersion and controlling flocculation and so forth.
Okay. And we can have a last question. Does choosing a lighter color, like white color, in hot regions like Qatar or Gulf countries, let's say, reduce potential paint problems?
Well, certainly white or silver will reflect better than, say, a dark color, but you can now get pigments so that you don't you get more reflection and less absorbance. But if the coating reflects the sun, you certainly will have it will have a longer life than if it absorbs. There's been quite a lot of research in this area in recent years. I could, if anyone's interested, I could send me an email and I could send you more information on this. But there certainly are some pigments now that help regardless of color.
Okay. Thank you, Dr. Schoff. It was very nice to be with you here in this Congress.